This is an articulated boom lift. So it's got several actuators, and some of them are used for stabilization and some of them are used for actuation. So first thing we've got down here is this bottom boom. So the yellow part can raise up and down, and the orange part extends in and out. Then this black cylinder right here will stabilize the top. So this sort of diamond shaped thing, that has to always stay in this vertical orientation. So the black cylinder will keep that vertical no matter what the bottom part of the boom is doing. So then this next cylinder up here raises the top boom, the one that says JLG lift. And then the orange part extends in and out. And then in here, it's kind of hard to see, but there's this little tiny cylinder that will maintain the orientation of the basket. So this little tiny cylinder is connected to this black diamond shaped link, and it keeps that in the same orientation as a cylinder that is in here. It's kind of hard to see, but it's behind this orange link. The cylinder can extend and contract to raise this basket up and down. So there are 5 actuators on there, and 2 of them are for stabilization and 3 of them are for actuation. So now let's break this down into links and joints so we can just get a good diagram of all that. First, we'll do the cylinders. So we've got this cylinder down here. It's connected somewhere down here and somewhere up here. So revolute joint on each end. Then this bottom boom is also connected down here, and it extends all the way up. So we've got this, and then we have this prismatic joint, extends. There's another prismatic joint here. And then that cylinder has a revolute joint. So then the other side, this link is connected with a revolute joint there. And then we have this diamond shaped link, revolute joint for the cylinder, connects there, revolute joint for the top boom, which then has another prismatic to extend. Then it's connected here. So there's a revolute joint. This part's a 4-bar linkage. Then I'll get a different color to draw in. So here, there's that little tiny cylinder that's basically connected like this. And then there's another cylinder in here that can raise and lower that basket. So let's see, this one is for stabilization, and so is this one. And then for actuation, we've got here, 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 and here. So we'll treat this as 5 degrees of freedom because 5 of those cylinders are for actuation and 2 of them are for stabilization. So now let's break this down into a vector loop diagram and work out the math for it. So here we are at the whiteboard, and you can see that we have the kinematic diagram on the photo, and then beneath it, I've drawn in gray sort of a simplified version. So that's what we'll draw our vector loops on. we'll start with the bottom loop. So we're going to have 5 different loops because we have 5 different degrees of freedom. And we've got the cylinder that connects here to raise and lower this. So we need to put some vector loop arrows. So we'll say we go to the right and up. So this one here, we have R1, R2, R3, R4. So just to draw that a little bit bigger down here. And then up above, we'll have a magenta loop. So we'll make this one is for stabilization. So this one we'll say is R7, R8, R9. We'll put arrows on that. So then to raise the top boom, we'll make this loop red. We've got this cylinder here, and then we need to connect it. Here we'll have R10, R11, R12, and we'll draw that also larger. So then we'll do a green loop here. So this is stabilization. And this is R15, R16, R17. And then we'll do a loop for the basket. We've got this part, so we'll say this is R19, pointing up is R20, and that cylinder is going to be R22. So you'll notice I didn't quite number these consecutively, and that's because there's going to be some other vectors that connect them in between. So to get some of those other vectors, actually let's draw the basket loop a little bit bigger so it's easy to see. So then we need to connect these loops together. We'll do that with black. So we have our 1, 2, 3, 4. Now this here is a prismatic joint. So we'll need an R vector that goes to here, R5, and then another R vector that connects up here, R6. So then the magenta loop, we have R7, 8, 9. And then the red loop, we have R10, 11, 12. So we'll connect the red to the green. This is going to be R13, R14, and then we have 15, 16, 17. So here we'll need R18, we have 19, 20, and 22. So 21, we forgot one. Let's put 21 in here. So now that we have all these vector loops, then let's write the equations for these, and then we'll be able to figure out knowns, unknowns, inputs, constraints, all that sort of thing. Now, the black vectors are not actually going to show up in the loops because they're just connecting one loop to the next. They're not part of an actual loop. So we will need to use those for the simulation when we plot it and when we calculate the position in space of all of the points. But those are ones that we can just know and control. So none of them are unknowns. So for the blue loop, let's go around this one counterclockwise. We'll have R1 plus R4 minus R3 minus R2 equals 0. We'll have R7 minus R8 minus R9 equals 0. These are both 0 vector. Now the red loop will go clockwise, and we'll say R11 plus R12 minus R10 equals 0. And then for the green loop, also clockwise. And for that one, we'll say R15 minus R16 minus R17 equals 0. For the cyan loop, we will again go clockwise, R17 plus R18 minus R22 equals 0. And before we break this up into X and Y components, we're going to need a coordinate frame. So let's put the coordinate frame down here. So we have X going to the right and Y going up. We're going to assume that the base is parked, and so it is considered ground. So now let's break this up into knowns, unknowns, inputs, and constraints. For this system, we know we're going to get 3 inputs to the loops. And that's because our 6 here and our 14 here are not part of the loops, even though they're actuators. So the blue loop, the red loop, and the green loop, sorry, the blue loop, the red loop, and the cyan loop will all be actuated, and then the magenta loop and the green loop are for stabilization. So those will not be inputs, those will be unknowns. So for the knowns, we basically know the length of everything that is not a cylinder. So that is R1, R2, R4, R5, R8, R9, R11, R12, R13, R15, R17, R18, R19, R20, R21. We know all of those R's. Input cylinders are going to be R3, R10 is an input. R11, 12, 13 are known, R14 is an input. 15 is known, 16 is stabilization, so that'll be an unknown. Then R17, 18, 19, 20, 21, and then R22 is an input. So now for the thetas, we know the angles of the ground. So that would be theta 2 and theta 1. Some of these other angles are going to be constrained. So in order to keep the basket level, R20 and R17 must be vertical. So we know theta 20 equals theta 17 equals pi over 2. So those point straight up. Then also to keep that basket level, in that 4-bar linkage, since theta 20 and theta 17 are equal, also theta 18 and 19 are equal. We don't know what those are, but we know that they're equal to each other. Theta 18 equals theta 19. So then there are some more things that have to actually be known. Because of the diamond that stabilizes the top boom, then we have to end up with the angles of R9, R11, and R21. All are going to have to be known as well. because those are basically, they're constrained to stay in the same position. So we'll be able to measure those, and that is theta 9, theta 11, theta 21, because those are all on this diamond. So that's constrained. So they're constant. So then if we continue now with the unknowns, we won't know the unknowns for, or we won't know the angles for any of those input cylinders. So theta 1 and theta 2 were known because those were part of the ground. Now theta 3, we don't know. And then thetas 4, 5, 6, and 7 all are going to be equal. So we'll put down here theta 4 equals theta 5 equals theta 6 equals theta 7. And then theta 8 is going to be related by some constraint angle. We'll call that gamma, because it's still part of the same link as R6, even though it points in a slightly different direction. So that equals theta 8 minus gamma. So we'll put in parentheses here, theta 4 to theta 8 are unknown, but that'll all count as one unknown because we can calculate them off each other. So then theta 9 was a known. Now theta 10, we don't know. Theta 11 is known. Thetas 12, 13, 14, and 15, we don't know those, but they're all the same. So we'll put another constraint down here. Theta 12 equals theta 13 equals theta 14 equals theta 15. Add those to the unknowns. Theta 12 to theta 15. Now theta 16, we also don't know because that's for the stabilization cylinder. Theta 17, we know because that's vertical, and so is theta 20. Theta 18 and 19 are the same. We have that constraint down here. We just don't know quite what those are. And then theta 22, we also do not know. For unknowns, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll have 9 unknowns. And then we've got 5 vector loop equations. So we'll be covered because we'll get an X and a Y equation from each vector loop. And so that will be 10 things that we could solve for. So we're good there. Now here I have written out all of the vector loop equations and drawn the vector loops next to them. So it is easy for us to calculate. So first we're going to figure out position for each one and then take the derivative to get velocity, put that into matrix form so we can figure out the Jacobian. We'll need the Jacobian for programming later. So let's start with the blue loop. Now here, R1 is only in the X direction and R2 is only in the Y direction. So we'll have R1 in the X and negative R2 in the Y based on this equation. And then we need to add in the stuff for R3 and R4 as cosines and sines. So now if we take the derivative of this to get velocity, we'll have the X dot equation and the Y dot equation. And R1 and R2 don't change because those are part of the ground, they're constant. Now R3 changes length and angle because that's a cylinder. R4 only changes angle. So now let's write those out. Now putting these in matrix form, we'll have a 2x2 matrix for the Jacobian. And then we will have the matrix of unknowns, which in this case is going to be theta 3 dot and theta 4 dot, because R3 is our input. So we'll put the R3 stuff over here, R3 dot C3. Remember the sign changes when you move it to the other side, R3 dot S3. And then the Jacobian, just for reference, J theta dot equals B is the matrix form we're trying to get to. So the Jacobian will just have the coefficients here, which would be R3, S3, negative R3, C3, negative R4, S4, and R4, C4. So then for the magenta loop, R7 will change length and change angle. R9 is going to have a fixed angle because that was part of the diamond. And R8 is going to be known because R8 was related to R4 by a constraint before. So actually, let's write in our the stuff we know from the previous constraint, which here is going to be theta 4 equals theta 5 equals theta 6 equals theta 7 equals theta 8 minus gamma. That was a constraint we had worked out earlier. So now we'll know theta 8 going into this magenta loop. And then we take the time derivative to get velocity. And remember that the R9, theta 9 stuff, that's going to be constant again because R9 is constrained. I'll just put little hash marks on it to remind us of that. R8 does not change, theta 8 changes, R7 and theta 7 both change. So then let's put this into matrix form. So we'll have a 2x2 matrix for the Jacobian. Then our unknowns here are going to be theta dot 7 and R7 because this is a stabilization cylinder. So we don't know that length, we have to calculate it. And then the inputs are going to be the theta 8 and R8 stuff because that was something that we calculated previously with the constraint, so we now know it. So now for the red loop, the R11 stuff is all going to be known because that was also part of that diamond. So then the angle and length of R10 are going to change in just the angle of R12. Let's write out X and Y equations. Then we'll take the derivative to get the X dot and Y dot. Now, since R11, theta 11 are constant, then those will not have a derivative. But like we had before for the magenta loop, R10, theta 10 are going to change, R12 is going to change, theta 12 will not. So let's write those out. Now we need to put this into matrix form. So we'll have the 2x2 for the Jacobian. The unknowns matrix here will be theta 12 and theta 10 dot. So theta dot 10, theta dot 12, because R10 is an actuation cylinder. That's what raises the top boom. So the R10 dot stuff is going to be the input. So now we have the green loop. Our 15 here is drawn in the X direction, but remember that is actually the same as our 12. So we should write out that constraint. So once we have calculated the red loop, then we'll know that theta 12 equals theta 13 equals theta 14 equals theta 15. So that'll all feed into the green equation. And then we need to take the derivative of this. R17 stays vertical, so that won't have a derivative because it's constant. Then R15 changes angle and not length. R16 changes length and angle. So let's write those out. The inputs for this one are going to be the angle, the theta 15 stuff, because we had calculated that previously. So we know what that is. And then the unknowns for this are going to be that stabilization cylinder length and angle. So that will be the theta dot 16 and r dot 16. And then, of course, the Jacobian will just be those coefficients. So the coefficients, fill those in. And then the inputs is the R15, theta 15 stuff. So let's fill in that. Remember about the sign change when we go to the other side. So now finally here we have the cyan loop. So we write out our X and our Y equations. Remember that R17 is just in the Y direction. So we have that down here. And then R18 and R22 have X and Y components both. So now let's take the derivative to get X dot and Y dot. So R17 is going to be constant length and angle. R18 will change angle and R22 will change angle and length. So let's write those in. And finally, putting it into matrix form, we'll have the Jacobian. The unknowns are going to be the angles of R18 and R22, so theta dot 18 and theta dot 22. And then the input here is R22 because that's an actuator cylinder. So now that we've worked out position and velocity for all of these different loops, then we can put them into Matlab and do a simulation to see how this would actually look in real life. So we see it drive in, raise the bottom boom, extend the bottom boom, raise the top boom, extend the top boom, and raise the basket.